A quick introduction for the speaker. Alok is a software engineer at Google DeepMind, and he leads a team called Anthropogenic, which is focused on remote sensing and machine learning to solve urgent problems faced by the agricultural sector in India and the rest of the global south. He was a founding member of the Climate Trace Initiative, where he worked pro bono as a Google.org fellow with What Time. He has been with Google in various teams, including YouTube, Google REST for over 9 years, and he's worked in the tech industry for almost 15 years. And in the spare time, he leads a fairly large grassroots climate solution groups at Google of roughly 5,000 members who are collectively putting 20% time at work to build climate solutions in varieties of sectors. His interests include understanding creation of ideas and business models, evolution of governance, technology and empathy, and the resulting impact on society and collective behavior. So look forward to your talk.
Yeah,
Alok.
thank you, Nipun. I'll just quickly share my screen, and I think thank you for sharing those remarks. I'll kind of skip this part. Uh, so largely today, I think we'll cover. So I'll sort of try to limit the amount of technical work that I talk about, but I'll give you a lot more sort of background on climate change. Um, I think something that I do want to mention is that I when I started out, probably like 5 6 years ago, I started out without any real expertise in climate or agriculture or any of these domains. I was very much motivated by lack of climate action, and my sort of core interests are at the intersection of sort of the developmental needs of the global south, which is like bringing people out of poverty, increasing their income, things like that, as well as the need for climate transitions. Because climate transitions turn out to be complete re-engineering of every single uh, way in which society works, and it has to be reinvented in many ways. And so I think that's requires allocation of resources. And so how do you make that happen in a smart way is what I think I care about. So I'll sort of spend the first, so like there are like sort of 3 to 4 sections here. We'll sort of talk about climate change broadly, and then sort of have some understanding of solutions within the food and agricultural systems for climate change. And then this will also sort of motivate why we decided to work on problems that we are working on today, and the progress that we have made. There is an optional section if people find it interesting, and I want this talk to be very interactive. So if you want to work on sort of similar problems like we did, I can give you a brief crash course on remote sensing, and then I can towards the end talk about sort of engagement opportunities with DeepMind and Google Research broadly. So I think just talking about climate change, right? It's sort of there are like sort of 5 very simple sentences that I think I would like everybody to know that yes, it is actually happening, and we are causing it, and we are really sure that this is happening. Things are bad, but we can fix it. Um, and so, coming to some parts of the science, what you'll see is largely there is a number of gases called greenhouse gases which sort of warm the earth. And it's sort of a section of the complete electromagnetic spectrum that exhibit this behavior. Uh, and so when light enters from the sun, a lot of it gets absorbed by a number of these gases. And so they have like some special properties in which they capture these rays and then re-emit them, not towards space but in arbitrary directions. And so when those get captured, it leads to capturing of sort of those waves, right? And particularly those waves also happen to be the infrared waves, which are again the cause of warming. Had they been in some other ranges, it would not have mattered. And so there's like some special sort of physics which sort of only affects gases that have sort of three atoms and like a specific structure. Um, and when they bend in, so when the rays hit this molecule, sort of electrons get excited, and these bonds sort of bend, and then they re-emit. So there's like sort of deep physical reasons as to why only these gases exhibit sort of greenhouse gases. And so largely, I think greenhouse effect is actually good for the Earth. Had it not existed, we would have been either very cold or very hot, depending on if we were facing the sun or not. I think greenhouse gases act as a warm cocoon that keeps the Earth warm and livable. Uh, but I think, like, when things are not in balance, like, when they are not in balance, as in the amount of energy that's hitting the Earth should be the amount of energy that's sort of getting emitted in a steady state. So when that steady state does not exist, the sort of energy on the Earth continues to increase, and that's sort of primarily because of this greenhouse gases, which are capturing the energy and re-emitting it back to the surface. Uh, and so, largely, there's a term called radiative forcing, which basically means how much excess energy is getting trapped. And it's sort of the root cause of sort of increasing in sort of temperature, and then all the consequences after that. So sort of this is like a simple plot which is not actually, like, quantified, but it's sort of indicative to help you understand what is happening. So in the business as usual scenario, our emissions are going up. And as emissions go up, the concentration of these greenhouse gases increases. As these sort of greenhouse gases increase, the corresponding radiative forcing increases, which sort of ends up increasing the temperature. And so if the emissions go down to zero, the concentration also doesn't go down immediately, right? So largely, uh, because the concentration is the part that's going to drive radiative forcing, which in turn is going to drive temperature, basically, to actually drive down temperature and come back to normal, we need to go into negative emissions territory. And largely, temperature is a very lagging indicator. The temperature that's going up now is because of emissions that have happened in the past. And so, like, generally these forces move slowly, but then I think, like, we need to have a longer time horizon to draw things down. This is like the Keeling curve, where I think, like, we have been observing for the last almost 50, 60 years, temperature, like concentrations of carbon dioxide going up in an observatory in Hawaii, and then also corresponding temperatures going up uh, along with these emissions. So now, coming back to sort of the non-science, but like the facts in society, is that many countries like India are, which are called the global south, like the developing countries, are in a stage of rapid economic growth, where I think our economies are growing rapidly in terms of like per capita GDP, and, like, people having more empowerment because of it. And increasing per capita GDP is actually a good thing, where people have more access to resources, more access to well-being, and improved lifestyle. But unfortunately, as per capita income goes up, so do the corresponding emissions, because we start consuming more resources. Which is that, like, if we did not go out much, we start going out, we start flying, we start sort of ordering more things over any of these services like Zomato's or Amazon, or whatever have you, right? We just start using the available capital to improve our life, which ends up leading to emissions. And so if you see, India today is the third largest emitter, but in per capita terms, we are almost a pre-industrial country. And so the big problem is how do we continue to improve people's lifestyle without becoming a even larger emitter, because there isn't that much room left. If you look at the total emissions that have happened so far, largely what you'll see is US has been responsible for the vast majority of it, followed by Europe, and then more recently China. India, with 1.3, 1.4 billion people, has had the same emissions as less than 90 million people with less than, I would say, 50 I think 90 million people between Canada and South Korea combined. So I think we are sort of using less resources, but I think we can't afford to have the kind of lifestyle that people in the West have had. Um and this is a very sort of tough situation. So if you look at what UNFCCC, which is like the main original sort of climate conference that happened, I think it had sort of some equitable uh, allocation in terms of who is responsible for addressing climate change, which is that like it'll be on the basis of equity and in accordance with their common but differentiated responsibilities and respective capabilities, and which basically in sort of parlance means that sort of the richer countries have caused climate change more because they have emitted more and are therefore disproportionately responsible for addressing the effects of climate change. But in reality, that doesn't actually happen. What ends up happening effectively is, think about it as an analogy where, three friends buy a Ferrari, and two of the rich friends take it for a ride, get it wrecked, and then ask the poor person to pay for it, right? Because even though the original agreement in 92 said that that's what's going to happen, where the richer countries are going to be responsible, that actually hasn't happened. And we already see like really severe consequences of climate change, right? Across these different spectrum, things are continuing to get worse and worse. So whether we talk about sort of coral life, mangroves, fisheries, coastal flooding, river flooding, crop yields, like all of these things, right? In India, particularly, heat waves and heat wave related mortality is going to become a bigger and bigger risk as time goes on. And I'll just rush past this. There'll be a lot of sort of displacement because of sea level rise or extreme heat weather, where people's their current locations of residence will just not be livable in the future. There'll be sort of severe droughts. We're already seeing a lot of this. There's ocean acidification, and there's loss of our ice from the poles as well as from the third pole, which is the Himalayas. There's sort of extreme fires that end up causing these complete hazy and smoggy atmosphere, and like this is just the Bay Area, but we see that in Delhi quite often as well. So all of this is going to become the new normal, and not only that these will be happening in isolation, but it's quite likely that there will be cascading failures, as in multiple simultaneous vulnerabilities will occur. But I think despite all of these things, we should sort of keep our eyes on the prize, which is that what are the sources of emissions, and try to bring all of those down. So you can see that like the vast majority of it is coming from energy, and transportation and buildings, and this 25% of the section, which is called agricultural, forest, and land use, right? And so there are a couple of ways of thinking about this as to how you address this, right? You can decarbonize using either policy methods where you can say, hey, from tomorrow, everybody needs to put solar panels on their roof, right? So you can mandate it by law. The other way is you can financially incentivize things, as in you can say, hey, we are going to put like sort of reduce the cost of solar panels or electric vehicles, something like that, right? The other approach is building new technology. Uh, so there are like a number of ways in which I think people have talked about this, and I sort of firmly believe that I think technology has a major role to play in addressing climate change, because the policy and financial instruments by themselves are very incomplete. And technology also has the opportunity to make this transition very equitable. So largely, there's like sort of two things that we need to do. Solutions that are mature need to be deployed rapidly, and solutions that I think are needed but are not there yet, I think we need to fund research in that quite significantly. And I think the goal, like I had mentioned before, like for a country like India, where the vast majority of people are still sort of on the borderline of poverty, and I think we have like sort of a dual challenge. One is that we have to sort of meet our developmental needs while also decarbonizing, and no country has done both of these things simultaneously, and we'll likely be the role model for every other country, particularly say countries in Africa, and some countries in Southeast Asia as well as South America, in sort of decarbonizing in their future. So the main point that I want to highlight is that we need to leapfrog the sort of things that we have, leapfrog, for example, in say the payments and identity with our digital infrastructure like UPI and Aadhaar. We need to do more of that. And so I'll just quickly sort of shift gears and talk about how Google thinks about climate change, right? I'll quickly play a small video and talk through things. Our journey began in 1998 with the company was formed, but since 2007, we have been completely offsetting all of our emissions. Long before this became we started procuring very large amounts of renewables. We became the largest consumer of 2017. All of our hardware is getting produced with renewable sources. 2020, the next big challenge that we set for the next 10 years was to completely eliminate emissions in every hour of every day. It was a much, much, much harder journey than just net zero. We call this carbon-free energy. So I'll just skip past this. So I think I'll just talk through things if people didn't hear, but I think I think we've been carbon neutral since 2007. And I think we are aiming to be carbon free by 2030, which is a much harder challenge than just the mere net zero. So largely, I think our sort of strategy has like three pillars, right? One is leading at Google, which is making sure that Google's own impact on climate and environment is sort of going down towards zero. The second pillar is we build new solutions that empower our partners, whether it is, say, governments, researchers, academics, policymakers, everybody, nonprofits, to be able to sort of address climate change. And then the final third pillar is our existing products, which is, say, Android, Chrome, Google Search, Gmail, all of these solutions. Google Maps have more climate solutions inherently integrated into it, right? So I'll talk through these things. So leading at Google basically means our data centers are carbon free, our offices are carbon free. We are whatever say water we draw, we are able to rejuvenate more than that through rainwater harvesting and other mechanisms. Our products that we make, our devices, are also manufactured in a way where we are recycling plastics if we use them, not using other sort of resources that are damaging the environment and climate. And so I'm sort of skipping past lots of slides, but I'll just quickly highlight why carbon free is hard. So carbon neutral basically means that we emit something, but then we offset it. You can offset it by planting trees or many other ways, right? And all of which uh, I think offsetting is has been gamified and doesn't actually lead to long-term solutions. The net zero term or 100% renewable term basically means that on an annual basis, whatever carbon emissions you had, you have consumed, have um, sort of generated corresponding amount of energy. So say I sort of during the daytime was able to generate, because of solar, an additional 2 gigawatts of energy this year. I might have consumed 2 gigawatts of energy at night, right? Which compensated for it. But that's again, doesn't really help us avoid emissions, because nighttime emissions can never be recovered from solar, right? When we actually need energy. And so carbon free is a much harder bar, because it requires us to have every hour of every day in every location where we have our data centers or offices to generate the corresponding amount of renewable energy that we consume. This is through storage or in renewable sources or anything else. And nobody else has actually demonstrated that this is even possible, and we are trying to do it at a scale that is sort of unprecedented. um, and so anyhow, this is our target for 2030, and we call it 24/7 internally, 24/7 carbon free energy. The other sort of pillars that we have are sort of building new solutions by supporting partners, and the third pillar is around sort of say with Google Flights, Google Hotels, Google Maps, all of these, Google Search, having more and more climate solutions integrated here, right? So this is where I'll sort of shift gears and talk about my journey. I sort of moved back to India to work on the intersection of sort of my interests and the interest of India, where I think I was asked to, hey, for India in terms of climate change, agriculture seems like the right place for us to work. And so I was given a fairly open mandate to figure out what we should do in agriculture, right? And this is sort of now my journey in terms of exploring the entire space and then coming up with sort of problems that we should pursue and what we have done so far, right? And so a lot of this is when I get to the real work, I'll start sort of telling you about my team and what they've done. But this is just the background around agriculture here. And so there is no pathway in which we are able to hit, like, say, the global 2050. India has like a 2070 target for net zero, without addressing agriculture, right? Agriculture has like large emissions. It's sort of responsible for about a quarter of the emissions. It uses half of the usable land. There are also uses like 70-80% of the fresh water globally. It also is a large cause for air pollution as well as water pollution, because of runoff of fertilizers or burning of stubble. Uh, and so the thing is that for energy sector and transportation sector, I think electrifying the ecosystem, depending on renewable energy, seems like a well understood path. It's just scaling that up, and related innovations is what's needed. But agriculture is a very hard to abate sector. There are no clear solutions that truly scale. And so therefore it's sort of more heterogeneous, and that's sort of what we are trying to address. And if you think about there are like different ways in which you could slice and identify solutions in the agricultural sector. You can try to reduce the demand. So a lot of emissions come from, say, consuming animals, because they sort of generate methane. So if people move towards plant-based diets, that could actually help reduce that. So it's either they move towards plant-based diet or reduce, instead of meat, have fake meat. But like none of this is really important for India. We, like people in the global south, don't consume as much emission generating food produce. The other thing is uh, how do we increase the supply without increasing sort of more deforestation, more land usage? And so that can be through improvement of yield, sort of detecting pests and diseases early, and addressing it, reducing food waste by improving supply chain, reducing food waste by identifying spoilage early and consuming that, right? And this seems like a very easy target for us to go after. Like 6% of the global emissions entirely come from wasted food, right? Then there are things like, can you have different practices in which emissions are generated from, say, agricultural practices like rice production, by having sort of more agroforestry, intercropping, avoiding, say, stubble burning, planting sort of agriculture along with solar panels, um, sort of reducing the amount of emissions because of reducing fertilizer use, sort of using hydroponics, vertical farming. Uh, and then there is optimizing irrigation, rainwater harvesting, assessing crop damage because of extreme weather, uh, improving soil quality by sequestering carbon, by having, new varieties of crops that are able to have deeper roots, that are able to improve soil quality, and also actually gene editing, which are again able to adjust the amount of sunlight that gets reflected, or having new varieties that have higher yields or are able to withstand extreme weather, diseases, things like that, right? So there are like no single solution is a silver bullet, but we need all of the above in different combinations. But if we had to invest, how do we decide where we invest, right? And behind all of this, we need a digital layer that's the core underpinning that helps us experiment, measure, monitor, and deliver decisions that are data driven. So I'll talk about this sort of single slide that focuses on agriculture in India. Look at the Wikipedia table on the right. You'll see the productivity in India compared to the most productive country. In most cases, you'll see almost 3 to 6x difference. What you'll notice is that is uh, should be a major cause of concern, because I think we have chronically low yields, which are actually addressable by just better access to information, better access to resources. Uh, as a highlight, agriculture is 16% of the GDP, but employs over 40% of the population, and 60% of our land in India is critically low on water, primarily because of over extraction of water for agriculture. And if you look at the farmer population, right, the small sliver of 18% is able to consume 56% of the value. So there is like a creamy layer of farmers that are into sort of plantations and horticulture. Great for them, right? Like I think they have the access and technology. But the vast majority of farmers are highly underserved. They are not being able to derive as much value from their land as they could. And we need to build solutions like that truly address this bottom rung, and they need to be very, very cost effective and simple, because these farmers don't have access to that much technology. And then when we looked about funding and the situations in funding, we looked at who spends the most in agriculture, and we found that the government usually is the largest player. And what we found out is just the central government, like state governments have additional budgets, but just the central government spends over $100 billion every year in agriculture. But we don't see proportionate outcomes. And largely, this is because not that funding is the key problem, but targeting is the key problem. So, what we want to do is build solutions that can support targeted data driven evidence based allocation of resources. And that's a mouthful, but I'll explain that. Um, so, before we go further, I would like to take questions on the first part if there are any questions.
Okay. Any questions? I have one question. You had mentioned gene editing and GMOs, but
Mhm.
we also know that there might be some side effects like increasing the glycemic index, for example, for rice, etc. And many of those side effects are like noticed later. So what is your views on like fiddling with such things?
Uh, I think I think every farmer continues to fiddle with crop varieties, right? Like, we have always done it. This is not a new thing. Of course, the new capabilities that say CRISPR, Cas9, and others allow us to do is like, deep interventions. But like, the Green Revolution, for example, that happened in India was also a fiddling that we did, right? But that was because like, the vast majority of India was living ship to mouth. Like, we had famines and other things in the 60s.
Mhm.
So I think those situations are quite likely again,
I
because
see.
as temperatures go up, productivity of crop will go down. And so I feel I feel there are risks no matter what we do. I think, like, just saying that there is a risk because of GMOs is not the only risk. Like, if we don't do it, there are also risks. And so we should be able to have research in all directions. And then once we have a variety of solutions, because if the situation is very complex, you don't want to depend on only one solution, right? uh, you want to have a array of solutions, and then, like, change directions based on as you find out new information. uh,
Okay, got it. Got it. And I had another question. Perhaps you might already have this in your plan.
Mhm.
So as the country progresses, and you mentioned the green revolution, and will go through the different kinds of changes, and because of weather induced, the climate change also will induce certain changes. So for example, will that do you also see a change in the food habits, like the rice versus wheat debate, or the divide which has been existing? Will that also change, do you think? So just your broad views on that.
uh, so I can tell you what I see in data, which is that as people have become richer, I think, like, historically, I think they're just people who, like, we consumed a lot of wheat and rice, but
Mhm.
then I think pulses, vegetables and fruits consumption increased. And now what you see is, say, for example, poultry consumption has almost gone up by a third in the last 7 years, right? And so as people become richer, their sort of food habits are changing, and that's just like, it's not just true for India, but it's true about any country, based on their per capita GDP.
Mhm.
uh, will be able to, you can say what their food habits are, quite literally.
Okay.
All right.
Any other question? Okay, there are no other questions. You can go ahead, please.
Great, great, great. So then I'll just quickly jump into this part where, so Anthrocrishi's mission, as we talked about, is basically enabling this targeted data-driven allocation of resources. In brief, if you want to just a one-slide takeaway, is our mission is to organize the agriculture information at the smallest unit, which is the farm field. And how are we going to do it? Using machine learning. So I'll just quickly jump into our demo, and hopefully you can see my screen. Right?
Yes, we can see us.
Okay, great. And so I'll just randomly go in one of these areas. Hopefully it's an agricultural area. All right. So if I hide everything, Uh, okay, the caches are not fresh, but hopefully, yeah. So what you see is basically this is a standard satellite view from Google Maps, right? But if I just turn on just the tree layer, you'll see that we are able to identify all the trees. Come on. All right. I think the demo gods are unhappy. But largely, I think if I let's say turn on, so yeah, there we go. So you can see, like, we are able to segment trees reasonably well. And then, like, if I just turn on, say, the wells layer, you can see that we don't get all of them, but like this is actually a well. Like, these are actually wells. And our best performing class is usually our field boundary class, where we are able to identify uh, fields and oops, yeah. And then a second capability that we have is identifying crops. And if I click on a field, what you'll see is we've given a unique ID to every field. We know how big it is. We know the sowing and harvest date and what crop is growing. Of course, we don't update this demo every week. I think, this is sort of out of date data, but it's real data. It's actually what our models predicted, right? And then you can see that we have data for a number of fields, and along with it, there is confidence levels. In future, I think we want to connect it with other sort of data that's available in Google Maps, like distance to road, water, village, wholesale markets, cold storage locations, processing plants that are contextually relevant to the crop that's growing, and also create this multi-year uh, event history at the field level, which will have like what crop was growing in every season, what was the sowing and harvest dates, when sort of single events like, say, stubble burning or flooding or tillage occurred. All right. And I think, this sort of demo has been shown at many sort of events like Google for India, and has been seen by, say, this is our APAC president for Google, and Ashwini Vaishnaw, one of the ministers. Modi and Sundar have talked about it. Modi has tweeted about it, and highlighted how, agriculture is really important use case for AI in India. So our engagement model is we create these data layers, and we share it uh, sort of publicly through an API or other ways. And we don't have any PII tied to it. These are just polygons and associated properties with it. But then governments or any other private organization, or can use this data uh, and connected with, say, their sort of citizens, residents, sort of, and by linking it with those things, can then sort of provide interventions in a data driven manner, right? So, I'll, like, any questions again at this part before I jump into the technical side?
Are there any questions? I think they're all engineers. I'm waiting for the technical part.
Okay, all right, great. uh, so you can see my slides, right?
Yes, we can see a slide. Agriculture landscape is complex.
Yeah. So largely, agricultural landscape is very complex, right? India has very, very small fields. They depend very sort of, like, not just are they small fields, but there's a diverse usage of land. So for example, just in this image, you can see that there is sort of trees, there is farm fields, there is wells, there are buildings, there is sort of, fields that are used for growing sort of plantation trees, which we call orchards. There's also, a river, and then there is a check dam, and then, just like we had single trees here, you have like a dense cluster of trees, right? And so our goal is to go from this image on the left to a digitized output here, right, using a machine learning model. Now, note that I think this problem statement itself is a hard problem statement to come up with, given all the different solutions that we could have built, right? But once you have this, how do you evaluate that you're good? Even if you had like the most perfect model, right? Uh, it's also not clear. and and so where do you start is also not clear. And so what we did is we decided to rely on our internal imagery, which is higher resolution, but it's sort of private imagery that Google has procured from satellite providers. And we generated our own annotation guidelines and had annotators annotate it manually, right? All of which is sort of a non-trivial amount of work. Uh, and then we built a model, and that sort of had a specific encoder decoder affinity mass based architecture. And I think our architecture is sort of because this is a multi-class panoptic segmentation. We have sort of one layer which is a semantic layer, and multiple affinity branches that help with instance um, sort of segmentation. And we get sort of reasonably good results. But I think the hard part is not building the model or other things, but how do you actually validate? I think people will not adopt your solutions unless you are able to validate this data and demonstrate that this is actually good. And so in standard machine learning techniques, right, you hold back data and you split it, and that's what you use. But normally, I think there is sort of two other ways in which we have had to do our validation. One is comparing it with government statistics, right? And the second is sort of using this data for downstream use cases, giving this data out to partners. And so far, we've worked quite closely with a number of governments, like the central government, state governments of Maharashtra and Telangana, and IIT Bombay as an academic partner, along with Princeton in the US. And they've done a number of things here, which we'll get to. And with these three different ways of doing validation, I think that's when people feel quite satisfied that these results are really good. And then you deploy sort of a sort of solution at scale. Here also, it's sort of a non-trivial amount of work, right? Because these images from satellites, um, there isn't a single image that covers the entire region of interest, all of India, for example. So we have to depend on multiple images. But then these images are not capturing the entire country at the same time, uh, because all of they depend on satellites that are sort of covering the country at different time periods. And so seasons could have changed, other things could have happened, and these sort of images intersect with each other in very arbitrary ways. And so what we do is we sort of divide any region of interest in a gridded manner, and then we take sort of all the images for a given time period where we are trying to run our models, and sort of take all of those images. Some of them could fully be covering that grid. Others could only be partially covering that grid, right? We run it through our model, and each of which also generates all of these inputs, which have the semantic segmentation as well as the instance segmentation branches. Now, there's sort of, again, sort of a lot of engineering that we have to do here in vectorizing this data, deduplicating, merging, and creating like a single synthetic layer that is exposed to our downstream users. And then there is sort of like some post correction that we need to do, because a segmentation model could have aberrations, and so we sort of smooth these polygons and then add additional properties, like sort of specifying what the centroid is, what type of feature this is it a field or a tree or a water body, and just embedding all of that output in. And now we have launched this API, which you can see at agri.withgoogle.com, right? And you can see developer documentation out there. We were able to launch it last year. And I think if any of you want to use this for any sort of even academic use case or otherwise, we would love to have you use this. So data is partitioned by this gridded features that we call S2 cells. So each S2 cell sort of covers, so like we take a level 13 S2 cell, which covers roughly a kilometer by kilometer area. And we give you all the fields and trees and water bodies that our model is able to identify in that 1 kilometer by 1 kilometer region, right? And then there's a corresponding archive paper that you can look at. And then I'll just quickly walk through a couple of use cases that our partners have used this for, right? So IIT Bombay has been working with the government of Maharashtra, like the Department of Land Records, and what they've done is they have these 50, 70-year-old paper maps of ownership that were done using that were created using manual surveys, people actually walking across every field and plotting it. And then they have a tabular record which has mutations, which is like, like this land was subdivided into so many pieces because of inheritance or because of selling, buying, merging, all kinds of mutations. And so they have those two pieces that they have access from the government. And then they have our model outputs, right? And so they sort of synthesize all of these three outputs into a single uh, layer, which digitizes these land ownership. And what they find is upwards of 50% of the fields they are able to digitize without human intervention. And they can also identify places where they are not able to reconcile things because land has changed so significantly in the last 50, 70 years. Like rivers have moved, buildings have come up, roads have come up. It's just a lot of change that has happened. Another use case is because we have multiple classes, we can measure how much tree cover there is along field boundaries. And generally, I think there are concerns when you talk about reforesting a land, particularly by using agricultural area, because if you try to scale that up, it is obvious to understand what happens is the population doesn't really change, and people's food needs also do not change. And so what happens if you convert a lot of agricultural area to tree cover is some land somewhere else is going to get deforested, right? Because people's needs for food continue to remain. And so there are concerns around permanence, additionality, which are sort of again scientific terms in the context of carbon emissions, etc. And so, but what is interesting is if a land was not being used, using that for planting trees is generally considered a good thing. So the land between field boundaries is usually sort of something where you could plant trees. And we try to measure using our model output what the current coverage is across all of India. And that turns out to be roughly the size of Croatia. But there is almost a 7 to 8x increase that is possible by just incentivizing it somehow. And our models now have the capability to monitor it and support it, right? So that's the first thing here. Any questions on the technical pieces on the first solution that we have?
Any questions?
All right.
I had one question.
Yeah,
So
please.
when you do the segmentation, are you just using the RGB imagery, or are you also using some other modalities, or let's say
Yeah.
SAR or anything else?
Yeah. So the first piece that we talked about, it is using just the 30 centimeter RGB imagery only. At 30 centimeters, we don't have other bands, or at least historically haven't had other bands. I think there are more recent satellites that have additional capabilities.
Right.
Uh, yeah, I think if we are interested in going into having a deep dive in the remote sensing part, I can cover some of those pieces later on, which will help everybody.
Sure, sure, sure.
But I think so. I think you already identified a problem with this high resolution imagery, right? That it's only looking at three bands. It also is that a problem that this high resolution imagery is not available in real time, right? Like this refresh rate of this data is not going to match the refresh, the rate at which agriculture happens. The agricultural every agricultural season, we are not going to have a new image because it's really expensive to have this data. But there also happens to be public imagery that is at a much lower resolution. So instead of 30 centimeters, at 10 meters, and this is available at a weekly cadence, right? So now, if you want to have this data available in real time, how do we do it? Uh, so can we use a time series of Sentinel-2 images at 10 meters and a sort of reference older 30 centimeter image that could be out of date to generate current field boundaries, again at at meter or sub-meter level accuracy? And so how do we do this is again sort of using super resolution. In fact, Aditi, who I think used to study at IIT Gandhinagar and worked with Professor Nipun, I think joined us last year as a pre-doc researcher, and she is working on this. And I think I'm not going to talk too much about it as to how we are doing it, but I think you'll see a paper hopefully later this year, early next year, around this. But that's the next effort in this direction, is how can we generate segmentation in real time, combining like a number of, like, not just Sentinel-2, but a number of these satellites that are in the public domain that have like weekly cadence of data to generate field boundaries, right? The second effort that we have is, given a field, how do you tell all the events that have happened historically on it? Like, what's the machine learning model that we can use? All right. And here, I think this is our landscape monitoring and event detection capability. And we are launching something here soon. We've tried a number of models here and have finally settled in on uh, uh, a transformer architecture. Again, along with this launch, there'll be something up on archive, and then later down the road a publication. But largely, I think crop classification models have a lot of for example, we worked with the central government's body called MNCFC, National Crop Forecasting Center, and they provide the underlying data which government uses for decision making. And what we found is, historically, they have built a single model for a single crop for a single region. So they may build, say, a sugarcane model for Uttar Pradesh, which is different from a sugarcane model for Madhya Pradesh, which is different from a sugarcane model for Maharashtra. And so our goal here was, how do we cover more crops than just a single crop? Like, actually, maybe even 10 crops, 30 crops, and have a single model that to begin with covers all of India, and then potentially expands at a much wider scale, right? And is able to generate not just like a single season, but have multi-season output. And so that's where we are in our journey. So we want to have geographical generalization, and also we want to have in-season crop identification rather than post-season. So in season basically means that we only have a little bit of the satellite imagery that would be available during the entire agricultural season, because the decisions that we need to make are usually within the season. So should this person receive fertilizer, in what quantity, in what proportion, like what how much nitrogen, how much different components of the fertilizer should be, things like that. Like, those decisions really require sort of near real time availability of data. And so around geographical generalization, what you'll see is with our encoder decoder architecture, we are able to get upwards of, I think, like, this sort of, these results are a little out of date, but uh, currently I think we cover like 13-ish crops. And our, like, the sort of experiments that we have run is by holding back data from certain regions, and seeing our performance in those regions, right? And we find that we are able to have fairly good accuracy, and other sort of metrics across the country for a large number of these crops, right? The other thing is also the in-season classification, where we have the post-season outputs, right? But we try to only give the model partial data, only the, say, like 0-day data, 30-day data, 45-day data, things so on and so forth, to see like, what our performance is with only partial data. And what we find is, like, generally around at the 2-month mark, we start seeing like really good results that are useful downstream. And as we continue to get more data, our performance increases. And so this graph sort of shows you different crops, how our predictions sort of are after X days. So the first one is at 0 days, the next one is at 30 days, 60, 90, so on and so forth, right? And then we also try to compare this with large scale evaluations, which is, again, look at government statistics for that region. And generally, I think what we find is they're mostly aligned. And then we looked at, again, like, validating on ground, which is actually a ongoing process right now. We've done this to some extent before, but there are other like, multiple partners that are again evaluating this output as we move towards a launch on the ground. And the sort of use cases that this actually launches is, this launch enables, is sort of like, instead of giving financial assistance, make that financial assistance sort of conditional, as in, like, for example, you only pay farmers if they actually sow something, rather than paying everybody. And you, in that case, can pay farmers even more, right? So instead of giving 5,000 rupees, can you give them 7,500 rupees? But I think you incentivize good behavior and disincentivize bad behavior. And it's not just for the financial assistance, right? You could do this for any other use cases, like providing loans, insurance, agricultural equipment, fertilizers, advisories, any number of solutions, right? And so the key piece here is timely access to information, to the sort of people who are allocating these resources. So anyhow, like, any questions so far on the second project?
Questions? So I had one question on this specific project that you're talking about. So this is more coming from, like, when I've heard about the crop fires, stubble burning, and somehow the statistics shown this year were that the farm fires are going down. And I think everyone was claiming that it's a huge success and the policies are working. And then another scientist found out that they were now bypassing, they were not like putting the fires during the satellite overpass. They were doing it when there was a blind spot. And then he used another satellite product, which was, I think, the Korean satellite, or I don't exactly recall. So do you envision any adversarial behavior in the, like you mentioned, for good incentive, bad incentive, wherever any money is involved, I sense there would be some scope of adversarial behavior. Do you see any of that with this, with your
Uh,
applications?
yeah, so far we haven't. I think we have tried it, but what we find is, I think this is a very complex situation because not only is it a major health issue, but the government also has made it illegal to burn stubble, but it is also hard to enforce those laws, right? And so it's a tricky situation, and I think we only want to have solutions out there after we are sure beyond reasonable doubt in having something out there. So I think it's going to take us a while before we launch something in this domain, right? So with that caution, what I'll say is, of course there will be adversarial behavior, and also what we need to understand is that farmers also have a reason, it's not like they actually enjoy burning stubble, right? And so the solution is not always to have like a stick, right? uh, I think what our goal is to have information available that allows for effective decision making down the road, right? And so policymakers will come up with different solutions. For example, making it illegal doesn't really change people's behavior. You can't just jail every farmer, right? Our jails don't have that much capacity, even if they wanted to, right? But like realistically, I feel the adversarial behavior is happening. Number of fires did go down, but the amount of area that was burnt did not change, and that actually is the main driver that that is sort of responsible for air quality, right? I think so. I think we need to figure out solutions that sort of can incentivize behavior, and I think there is like a new set of satellites called FireSat, which were originally built, and I think they were largely funded by Google, with the aim of addressing, say, the big fires that you see in California, right? And I think today for detecting fires, the satellite products that exist are either you have data every 5 minutes, but they are coming from geostationary satellites that are for 40,000 kilometers, 35,000 kilometers up in the sky, and so their resolution is in kilometer scale. And if you want to have higher spatial resolution, then you are stuck with the near Earth orbit satellites. But then they sort of rotate too fast, and so you will not have coverage at the same temporal frequency. And so what Google did is they built like custom sort of optics that can detect fires across haze and other things, and have a large constellation of satellites. And so basically there you will have output every 15 minutes, right? And at, again, sort of the size of Indian fields,
Mhm.
so that it's actionable for use cases like fires in California. But
Got
I think those data products will sort of make all of these problems go away eventually.
it. Okay. Got it. Got
All right, great. So I think one of our main problems with say crop classification or other things is a lack of good data, right? So even if we take say stubble burning as an example, right? How do we actually know that our model is good, right? Because for the segmentation piece, at least we could look at the image and have somebody annotated it and say that okay, this annotation appears to be good, right? But from satellite images, we cannot actually identify crops, and we definitely cannot say this field has burnt or not burnt. I think we may be able to identify active fires, but active fires are rare. But other events like, hey, did they apply fertilizer? What crop is growing? Is the land tilled or not? And so for that, I think we have had to pay people to actually go visit farms, and that is not a scalable thing. It's not a scalable thing, not just because it's expensive, but also there's a huge imbalance of data. What that means is there's too many sort of people who are growing, say, rice and wheat, but too fewer people that are growing, say, turmeric and coriander. And for a model to be performing well and being good, the performance in the majority class is important, but a model could be well performing if it just always says it's one of the majority classes, right? So you need to have a balance of what your performance is on the underrepresented classes. And so with that in mind, I think we really needed additional sort of sources of collecting data. And we have an additional project that has been exploring using of street view imagery. And so we have currently at a stage where we have a single model that's sort of using, say, natural imagery capabilities, like the ones that you would see in Gemma or Polygemma or Gemini or any of these sort of simple models that are able to identify crops, and then providing those as pseudo labels for our satellite model. I think as we are wrapping up on those experiments, our teams is also exploring building a joint street view plus satellite model. And again, this is a much harder thing. But again, I think what we feel is that this is a direction towards geo-foundational models that we are quite keen on. So any geo-foundational model, right? Like there are like four resolutions that satellites have. There is a spatial resolution, which is about how many meters on the ground cover a single pixel. So you see the image here is very blurry because the pixel size is larger, and here you see the pixel size is much smaller. The other is how often do you have revisits to the same place? That's the temporal resolution. Spectral resolution is which wavelengths of light do you cover? And radiometric is how many bits are available per band, right? And any good geo-foundational model should be able to assimilate data across any like you could have a very high spatial resolution, low temporal frequency data source, and any combination and mix of this, right? And be able to sort of interpret data across all of these. And anthropography pushes simultaneously on multiple of these dimensions. So for example, smallholder fields are much smaller here. Monsoon season, which is our main agricultural season, has a lot of cloud cover, and so we end up then relying a fair bit on satellites that sort of can penetrate these clouds using, say, synthetic aperture radar. And then we also are quite keen on detecting seasonal and sub-seasonal events. Uh, so anyhow, so coming back to if you see our data sources, right? There is satellite imagery that sort of at 10 meters, that's 10 meters, 30 meters, that's available at a weekly cadence. There is 30 centimeter imagery that's sort of at annual cadence in the best case. There is sort of street view imagery that's available every n years, and then there is a continuous data stream of weather. And what you see is like all of this data has a lot of heterogeneity across these spatial, temporal, and spectral dimensions. And the core capability that we are after is how do you take these different modalities and use it for addressing the climate solutions that we want to. And so far we have only pushed on the segmentation and classification pieces. But I think what we are also after is these event detection, carbon stock, and yield prediction, which require many of these modalities to be addressed. So, any questions so far, folks?
Any questions? No, I don't think there are any questions in this part.
Okay. All right. So I think we like would people want to build climate solutions using remote sensing? I'm just curious. Like, can everybody raise their hands? Just, everybody, just raise your hands. Right. Okay. Now, everybody who would no keep your hands up. Everybody, just keep your hands up. Okay. All right. So everybody who doesn't want to build, uh, or who, so everybody who wants to build even if it's a toy problem, right, with satellites, lower your hands. Okay. So okay. Now, there's a much better way of identifying who's actually
Yeah.
interested.
So actually, in some way, I'm forcing them, all of them, to do something because I've given them an assignment on SkySat dataset, object
I see.
detection. So they,
I
they
see.
have to do anyway.
Okay. Good. So what I'll try to do is, I think I had a tough journey in just understanding satellite imagery, and since this felt like a course where you may end up doing some of this, I just added a bunch of material that I use for, like, people who join our teams, or whatever else, to explain, like, give a little bit of background in remote sensing. So actually, there is a very substantial amount of remote sensing data out there, and this data is completely in the public domain, right? But the amount of research that has gone after, say, natural images, right, for doing sort of silly things that say Instagram or whatever else does, right, like creating filters and like all of these things, uh, has received disproportionate amount of compute, attention, research efforts, compared to, like, solving really hard problems that are urgent from a real perspective. And all of this data has been public for a very long time, right? So Landsat, which is like probably the oldest mission, has data since 1972. But these days, the workhorse for everybody who's working in this domain is usually by the European Space Agency, ESA, called the Copernicus or the Sentinel uh, constellation. Of this, probably Sentinel 1 and 2 are likely the most relevant use cases if you're doing land based analysis. There may be other satellites that do, say, some atmospheric or ocean observations. For any satellite, the orbit is destiny. If you are very far away from the Earth, you could be in a geosynchronous orbit where you rotate as the Earth rotates. But if you are very close to the Earth, you go around the Earth much, much faster. And so uh, there are sort of constraints on a satellite in terms of how much power it has, because it needs to sort of be able to capture data and transmit data and adjust altitude using either by burning propeller fuel or by using, say, solar panel generated energy, right? Uh, so that's one limitation. The other limitation is because of the orbits. And I think the two orbits that people have settled on is either the geosynchronous orbit, which is very far away, or the other orbit that's called sun synchronous orbit. And sun synchronous orbits basically mean that satellites cross the equator at the same time every time they cross the equator. So generally, sun synchronous orbits are roughly around between 500 to 700 kilometers above the Earth's surface, and a single orbit takes about 90 minutes. So, but like every time they cross the Earth's equator, it'll be always, say, 11 a.m. or 1:30 or something like that, right? So all data is always consistent. And so orbits determine quite a lot. Um, and then the type of sensors that exist, right? So there are satellites, like I said, are RGB only, uh, or there are satellites so all of these satellites, RGB, multispectral, hyperspectral, they depend on reflection of sunlight from the Earth's surface. which means that you'll generally have data only on the sun facing side, but no data when you're covering the night facing side. But then there are sort of other satellites that have an active sensor where they emit light and they receive that light. And so they will have data on both sides. So majority of them are generally the passive satellites. And then we covered the different spatial resolutions. We covered, say, temporal resolution. So for temporal resolution, I think one way of increasing, say, temporal resolution is by having a constellation of satellites, all of which are identical or mostly identical, having the same sensor, right? We covered this, and yeah, the spectral resolution I think is somewhat important. I think most of our phone imagery or others that we see is generally RGB, right? But satellites, like the workhorse satellites, usually are multispectral, where they have not just RGB but also infrared, deep infrared, things like that, right? So generally, you'll see at least 10, 15 bands that exist. But hyperspectral satellites are sort of quite interesting, but very much in sort of early research phase. But their capabilities are going to be extremely interesting from a research perspective, because what they do is they have, instead of 10 bands, they may cover the same electromagnetic wavelengths, but with extremely fine precision. So instead of a band being, say, 300 nanometers, each band could be just 4 nanometers or 10 nanometers in width. And so that allows for very specific information to be captured. So, like for example, in the case of agriculture, you not only can say it's rice, but you can say, oh, this is basmati rice, or this is what variety of mango, and that's really unique. There's also satellites that are synthetic aperture radar, which are one of the active sensors. So, something to look out for next month, hopefully, is a satellite called NISAR that will launch. This is the first partnership between NASA and ISRO, and it's likely to launch next month. And in fact, it is the most expensive satellite for Earth observation that's ever been built. Um, and so So these synthetic aperture radar satellites have historically been used for military purposes, but they increasingly have abilities that are useful for us. For example, they work in these microwave wavelengths, so centimeter scale wavelengths, and they are able to penetrate clouds. And so, for example, during the monsoon season, we can then see, oh, what is exactly happening in different fields, right? There are other satellites, or at least other sensors. For example, GEDI was a sensor that was on the International Space Station, which had lidar, which had like very high accuracy measurement of depth. Um, And then there is sort of very sort of standard things that people do, which is NDVI, which sort of is a measure of reflectance and chlorophyll content. But largely, the main point that I wanted to hammer in was that it is Moore's law for satellite imagery, because the amount of, because the price of launching satellites has gone down so much, we are going to see a extreme increase in the quality and quantity of satellite based Earth observation, while the prices for that go down. And so we are in this sort of golden age of remote sensing and machine learning, because machine learning hasn't yet played as much of a role as it could. Uh, and so it's a very exciting time in this field overall. So that sort of concludes most of the things that I wanted to communicate here. Before we go on to the engagement section. So, any sort of final questions that people have?
I've got one question. Like last some time before you have said like we can sense which type of mango it is. So how we are exactly sensing that what it is Alfonso mango or some other type of mango using the remote sensing?
Yeah, yeah. So we would of course not know if it's a mango on a tree, but we could detect the tree species itself, right? And what happens is sort of trees behave differently. Trees or any kind of vegetation. So say one kind of rice variety versus another kind of rice variety, their growth patterns are different. Their what they reflect is slightly different. So for human eyes, it may not be that clear, right? But if you look at this wide range of electromagnetic spectrum, I think if you remember this image here, yeah, here, right? So we actually look at, like, I think human visible light is just these I think like 400, 500 nanometers to 700 nanometers. That's the range which humans can see. But these satellites see a much wider range of frequencies. So roughly from like 300 to 2000 nanometers. And there are certain things that these satellites are able to observe that human eyes cannot. Does that make sense?
Yes, yes. So is there any study has been done like this specific tree has this at this spectrum behave something like this and the another
Yeah,
tree?
yeah. So that's sort of so like historically, everybody was using some procedural methods, right? So like for example, people build like indices like NDVI. So NDVI is basically taking like the near infrared band, subtracting the red band from it, and dividing that by the sum of both of those, right? And this is called a sort of normalized difference of vegetation index. That's what NDVI stands for. And there are many of these vegetation indices where they just combine these two, any two number of two or three, maybe in some cases, bands, and try to find some properties with it, right? And so NDVI particularly is the most popular one, which sort of has indicated how much chlorophyll content there is. And the classical remote sensing models were not machine learning based. They were very much analytical, right? And so what people would say is, oh, if your NDVI is between 7.1 to 7.3, you're likely growing rice. But if it's between 0.81 to 0.83, you're growing wheat. Like they had like these sort of very simple things that actually were localized to a region, but they did not generalize to other agricultural practices, to other regions. And so with machine learning, you don't actually depend as much on these um, vegetation indices. And you let the model learn from a very diverse set of underlying data.
Oh, good.
Okay.
So I'd like to just add to that. Whatever little discussion I've had with ISRO Space Application Center folks, so they've been doing similar things for a long time. And they also mentioned that when you're looking to differentiate between different plant species or classify between them, they also often end up looking at the time series of the data and not just a single times snapshot.
Right.
So if you look at the time series over, let's say, some 15 days, 30 days, you'll see that maybe the nitrogen content goes down or the water retention rate goes up, and all of that is nicely reflected in the, if you consider the entire spectrum.
Correct. Exactly. So it's a like it, almost always any kind of satellite based work is always a time series work, and so you would actually observe the NDVI pattern. Like there will be like a NDVI curve basically. And so oftentimes even based on the curve shape, people could say, oh, this curve is representing rice versus this curve is representing soybean or something, right? All right, any other questions, folks?
Any other question? No, there's no other question.
All right, so this now we get to the exciting part potentially. So there are engagement opportunities for students as well as faculty that I'll just sort of indicate here. So there are like fellowships for PhDs. There are sort of conference sponsorships. There is sort of student researcher programs where Students can join as interns with some of our research teams. There's also like a pre-doc role, which is a unique role for India, where we hire for the November, Jan, or like there's sort of 2 times in a year where we do hiring, and this is usually like a 2-year role. There's also what Aditi has joined us as, and so the hope is that people get good amount of industrial experience of research, they build something amazing, and also get some publications, and then after that, they move on to pursue their PhDs or other graduate studies uh, in India or abroad, right? So those are the various sort of engagement models. And then similarly for faculty, there is like a visiting researcher program. There's like different kinds of funding, like CSR funding, Google India Research Awards, cloud credits for research work, and then sort of like some Googler initiated research awards for working with our teams. Um, with that, I'll sort of stop presenting and thank you for this opportunity to engage with all of you. Hope all of you are able to find something passionate to pursue, right? Whether it is in climate change or something else. It's a pleasure.
Yeah, so let's thank Alok again. I think there were quite a few interesting things. So, firstly, I think the discussion you had on climate change and the basics, I think that was very new for me. Like, while while we understand the CO2 and the other gases and methane, etc., but understanding a little bit more about the physics of it was interesting. I think I would want to go back and read a little bit more and understand. And then the remote sensing primer, I think, was very interesting. I would have loved to have it when I was starting out. I But to me, the main takeaway was, which you passed up as a joke in between, that like the filters and all are getting way more attention than the urgent problems for which we have tons of data, and we just need people to spend time and energy on that. Okay, so with that, let's thank Alok again. Thank you.
Yeah, thanks. Thanks, for have a good one.